All right, so this is stuff you should have learned in middle school, but if not, I don't love this subject. It seems like we don't give you enough information to really determine the difference between a physical and chemical change, and maybe after some years of college you would understand the difference, but right now it just comes to grasping and listening to what your teacher tells you to write down, and it drives me a little nuts. So but you should know some of this stuff, and here we go. So a physical change would be the identity of the substance remains unchanged. So they're often reversible, but they're not always reversible. Examples being if you break a diamond or glass, it's still glass, right? If you weigh all the pieces before and after it's broken, it should weigh the same. If you grind something, if you cut like a piece of paper, it's still paper, it's just smaller paper. Phase changes. So anytime you freeze something or boil something or um, melt something, that's all a phase change. That's not changing the substance. Bending something, ripping something, those are all sort of things that aren't changing the physical identity of the substance. All right. Chemical changes are when a more substance becomes a new substance. Examples are burning it or rusting, molding, rotting, growing. We also call it a chemical reaction. And the key here is you will know if a chemical reaction happens if one of these four things occurs. And when we did the burning of or the lighting of fire of the iron filing stuff, the Brillo, that was a chemical change. And we know that because two of these things occurred. So bubbles forming or gases produced, that did not happen in that case. But if you see bubbles form, that's a good indication that there's a chemical change that occurred. What a precipitate is. So here we have a clear liquid and we have a clear liquid here. And when you mix the two clear liquids, you get this yellow solid, and that's called a precipitate. So if you see a precipitate when you mix two clear liquids, that's considered a chemical change. If you release energy, fire, or when we lit the steel wool on fire, it sort of sparked and whatnot. So that is an indication that a chemical change was taking place. And then this thing where color is changing slightly, and that happened also with the steel wool, that the color changed, but that is an indication or a change of smell, apparently, that a chemical change is taking place. So you'll need to recognize these as the year goes on when we do labs. If bubbles form, or, we may say, how do you know a chemical change occurred? And it'll be something like bubbles formed or sparks formed or precipitate or something. All right. The other thing we need to talk about is the difference between mass and weight. So we said matter is anything that has mass and takes up space. Mass is a measure of the amount of stuff and not so much what something weighs. So Mr. Roach has a certain amount of stuff in his body, and that doesn't change whether I'm on Earth or on the moon. However, if I go to the moon, I am going to weigh less, right? And that's because of gravity's pull on me. So scientists figured we need to figure a measurement that isn't going to be affected by gravity. It's just going to be what stuff something contains. And so that's why we came up with this kilogram gram scale of mass. And so mass will not take into account weight or gravitational pull, just how much stuff something has in it. So weight is a gravitational phenomenon and mass is not. Mass is just the amount of stuff that something is containing. All right. And then we talked about this. We talked about how you learn this in biology, that you can divide things into different little boxes. And that way, if you go in your backyard and you find something, you figure out which box it goes into. And this kind of classification is a very important part of science. So in chemistry, the study of matter, we're going to basically be on this side of this thing, but this is basically what we're doing, is trying to figure out what category to put things into. So the universe can be divided into either matter or energy, and energy can be kinetic or potential or heat or light, whereas matter can be divided into a pure substance or a mixture. Now you may be wondering, how do I know the difference of these things? Well, pure substances would come off the periodic table, either just one element, which would be one element, or a compound, which is a mixture of elements. A mixture, however, is going to be a more complicated uh, mixture or combining of things. And those mixtures can be either homogeneous, which means they have um, no interface or no borders, and heterogeneous, which means they have borders that you can see. So an example of homogeneous would be that clear liquid juice drink, and heterogeneous would be like sand, or if you put ice in that juice drink. You can see borders in both these cases, right? You can see where the sand rocks begin and end. That would be make it heterogeneous. You can see where these ice cubes begin and end. All right, moving on to elements. So elements can be either metal, metalloid, or non-metal. And it turns out the periodic table has this wonderful stair step thing, like here-ish. And this staircase divides the metals from the non-metals. So on one side there's metals, and on the other side there's non-metals. And it tells you right here, in case you were wondering, that the non-metals are the green ones and the metals are the blue ones. Hydrogen is a little bit off. It should be over here somewhere based on its metal character, but it's there for other reasons that we'll talk about later. But metals, if you ever forget this on the day of the test, just look around. This is exactly what the periodic table will look like, where the names are on there. So palladium, maybe you know that's a metal, or you know that zinc is a metal, or aluminum, right, is a metal. Lead is a metal. Iron is a metal. These are all on the metal side. So everything else on that side of the staircase would be a metal. And non-metals, you know, hydrogen or oxygen is a gas. Helium is a gas. You know that from birthday parties. So hopefully, you know, those are non-metals. And then the metalloids would be the things touching the staircase. The only one that's really doing it that doesn't belong is aluminum. Aluminum is a metal because it's aluminum. And you know what aluminum foil looks like, right? That's a metal. That's not a metalloid. All right. So that's how you can tell whether an element is a metal or a non-metal or metalloid. And then mixture or compound is determined by the law of definite proportions. A chemical compound contains the same elements in exactly the same proportions, regardless of the size or origin. So this was Joseph Proust who figured this out. And basically what it means is if you have a drop of water, water being H2O, that water, whether you have a jug or a drop, or if it's from Mount Everest, or if it's from the Dead Sea, it doesn't matter. Water is H2O. It has the same basic ingredients, right? It's the same no matter where you are. And that's not true of mixtures. Mixtures can be different depending on where you get them. So here I went to Greece a couple summers ago, and even though I don't understand any of this Greece stuff, I did understand what this was. And this is basically telling you the ratio of compound that made these things. So if I were to take, for example, mercury and sulfur and put them in a 1-to-1 ratio, I would have this stuff here. I would have this red stuff. And if I take copper carbonate and copper hydroxide and mix them together in that ratio, I would have this sort of aquamarine colored stuff. So even though I didn't speak Greek, I was able to understand the chemistry of this. And what this was telling me is the ratio of elements in this compound. All right, so here's examples of how we're going to do this. I will give you something like tomato sauce, and then you're going to tell me, is it a pure substance or a mixture? So tomato sauce, while it has elements in it, certainly, right? There's all sorts of different carbons and hydrogens and whatnot in there. However, it's not the same in any two places. So tomato sauce is definitely going to be a mixture. And then at that point, I'm going to ask you, is that homogeneous or heterogeneous? You're basically looking for some sort of border that's present. And if I tell you you can see all the spices and stuff in it, that would mean it is heterogeneous because you can see spices as interfaces. Potassium carbonate. Now, you can't know what potassium carbonate is because I'm not going to teach you that until like unit 4. So anytime I give you something like that, I'm going to tell you what the compound information is. And in this case, it's K2CO3. So it's two potassiums, 1 carbon, and 3 oxygens. But because of that, that hopefully is telling you that ratio is the same no matter where you get it. You can go to India, or you can go to China, or you can go to Pakistan, and you can get potassium carbonate, and it's K2CO3. So that is a pure substance, and in this case, a compound, because it has the same ratio. Nitrogen is an element and a pure substance. Hexane, exact ratio given, so therefore that is a compound and a pure substance. Gold, you know, is on the elements, so that's an element and a pure compound. A pure substance. Brass, now this is the tricky one, which apparently I don't know why we expect you to know this, but I didn't really know that brass is different. Apparently you get brass in one place, it's not the same as brass in another. So it is a mixture for starters. It is not a compound, and it is homogeneous because you cannot see where the genius, maybe that way. You can't see where the copper ends and the iron begins, or whatever it is. All right, so I'm going to stop there and allow you to absorb all that. And thank you very much.